Hello viewers, I'm Kausalya. Today's topic is circuit transients, and under the circuit transients we are going to discuss about oral transients, rise of current. So here this is the circuit diagram of an oral series circuit, and this oral series circuit is connected in series with the battery voltage source by a switch key. And ER is the voltage drop across resistor, EL is the voltage drop across inductor, and I of t is the current that flows through this circuit. So here the input voltage is assumed to be a step voltage. So what do you mean by step voltage? You see, this is the diagram of a step signal. Okay, this is the signal whose value will increase when the value of t is 0, and once the value of t is greater than 0, it will remain constant. Alright. So here this is what I had written here. The input voltage is a step voltage and it is denoted by E into U of t. So here U of t denotes unit step voltage, that is here the value given is 1. Then the next thing is, assume that the current through the inductor before closing the switch is 0, because as we all know, inductor and capacitor are the elements that stores energy. Therefore, here initially before closing the switch, okay, the current through this inductor is 0. So now we are closing the switch. Okay, let K be closed at the instant t equal to 0. That is, previously the switch is open, right? Now we are closing the switch. So once you close the switch, what happens? You see, our circuit gets modified like this, right? So here you may ask why we have drawn an open circuit. In the place of inductor, you see here it is an open circuit, because inductor is an element which does not allow sudden rise in current, right? Once the switch is closed, what happens? The current will start to flow. So the inductor at that instant, it won't allow sudden change of current, or in other words, it won't allow the current to flow through it. Therefore, it acts as an open circuit, right? So in the case of open circuit, what about the current? The current that flows through the circuit will be 0, right? So here the 0 plus denotes the instant after closing the switch, and 0 minus denotes the instant that is the switch is kept open, right? So here in both the cases, when the switch is kept open and at the instant when the switch is closed, what about the current value? It is 0, right? Now we are going to apply KVL to this circuit. So when you apply KVL here, right? So what is the formula? In a closed loop, sum of voltage rise is equal to sum of voltage drop. So here the voltage rise is E and the voltage drop is created by these two elements, right? So here you see IR, right? Voltage drop across resistor is I into R, and voltage drop across inductor is L into di by dt, which is equal to E. So here you may have a question, right? I said inductor acts as an open circuit, but while writing the expression, I had considered the voltage drop across the inductor. So, okay, be careful, you see. At the instant when you close the switch, when there is a sudden change in current, it won't allow, right? But once the current reaches its steady state value, then what happens during that time? Our inductor acts as a short circuit, right? So under that condition, we are framing this expression, right? I hope I had made this concept clear. We have considered this fact to know about the current, that is the initial value of energy that gets stored here, right? So this is the expression. Just we have applied KVL to this circuit after closing the switch, right? That's it. Now we are going to apply Laplace transformation. So when you apply Laplace transformation, you see here R into I becomes I of S plus L into this d by dt becomes S into I of S minus I into 0 plus, right? Which is equal to here E becomes E by S. So what is the value of 0 plus? Here I of 0 plus is again 0. So here we are substituting it as 0. Then the next step is you are taking I of S commonly outside. So our expression gets modified like this. So the value of I of s is given by E divided by s into Ls plus R. Now the value of I of s is, again just we are reframing. I am taking this L outside. When you take this L outside, our expression gets modified as s plus R by L. Right. Mark it as equation number 1. Now we are going to apply partial fraction. So when you apply partial fraction, you see we are rewriting this expression as a by s plus b by s plus r by l. Right. So here that is E by L are constant, okay, whose value will remain the same. So E by L remains as such. Here we are considering S and S plus R by L. So when you take LCM, right, so here both these denominators cancel each other and the left side we are having E by L. So here our expression is E by L equal to A into S plus R by L plus BS. Right. So here now we have to find the values of A and B. So when you substitute the value of S as 0, you can find the value of A. So when you substitute S equal to 0, the value of A is E by R. Again, when you substitute the value of S as minus R by L, what happens? We can calculate the value of B as minus E by R. Right. So we have calculated A and B. Now just substitute these values in our equation number 2. Right. This is our equation number 2. So just substitute the values over here. So when you substitute the values, you see here E by R is common in both these terms. So I am taking E by R outside. Here we have expression in the form of I of s, but what we need actually is I of t. So when you take inverse Laplace transform, you see this is our expression for I of s. It gets modified as I of t because we need only I of t. So when you take inverse Laplace, you see 1 by s becomes 1 and s plus r by l becomes e power minus r by l t. Right. So here finally E by R is nothing but our steady state current, which is denoted as capital I. Therefore I of t is equal to I into 1 minus e power minus r by l t. Okay, this is your equation number 4. Now the next thing is, so from this expression, right, so the steady state current is reached when the value of t is infinity, right. That is, you are turning on the switch and you are leaving it as such for some duration. And here L by R is known as time constant and it is denoted as t. But here we are having R by L, so this is nothing but our 1 by t, right. Now when you rewrite this equation in terms of time constant, capital I is equal to, we are just rewriting this expression, right. I equal to capital I into 1 minus, that is in the place of R by L, I am replacing with 1 by capital T. So this is our equation, right. So here in this case, again the same thing, when the value of t get increases, okay, the value of I also increases. Similarly, when the value of t is infinity, then the value of current, okay, this current, that is this small I will be equal to capital I, that is steady state current, right. Now we are going to calculate the voltage drop across the resistors and inductor. So here voltage drop across resistor is given by I into R, right. So here the value of I is, this is your expression for I. So just substitute here, write this R as such. Right, again I into R, it is nothing but your voltage. So here it is E into 1 minus e power minus small t by capital T. So now we are going to calculate the voltage drop across your inductor. So as we all know, by KVL, voltage rise is equal to sum of voltage drops in a closed circuit. So from this expression, now we are going to calculate the value of EL. So EL is nothing but E minus ER. So the value of ER just now we have calculated. So substitute the values, right? The next step, we are going to multiply this E with this element. So when you multiply, you see finally the value of EL is E into e to the power minus T by capital T. Now we are going to draw a graph, okay, for different values of ER and EL. So here in this case, again you have to select the value of t as per your wish. That is, initially let the value of t be 0. Then it is 0.01 t. Then it is zero point 0.5 times of, that is the value of t in terms of capital T. Initially it can be 0 and next it can be 0.5 t and it can be 1 t, something like that, right? So for different values of t, just calculate the value of EL. Similarly for ER also. So once it was done, you see here we are having a graph like this. Okay, this is your ER and this is your EL. Right. And once you look here for different values, again for different values of t, the value of current, it gradually increases and it reaches its final value. Right. The next thing is we are going to define the time constant. So the expression is I is equal to I into 1 minus e power minus small t by capital T. Right. So here in this case, substitute the value of capital T as small t. Right. When both the values are equal, what about the value of I? It is 0.632 times of capital I. That is, I is nothing but 63.2% of your steady state current. Right. So here comes the end of this derivation. If you have any doubt, let me know in the comment section. Thank you.